Okay, so shall we start? Okay, so let's continue. So, as I mentioned before, one of the things I'm trying to do is to make sure I finish a topic before the parts end. Like, I think I kind of managed to do that with oral, but with ML, like I'm still a little bit out of sync. So we have 5 more minutes of ERM before we jump to the next topic. Okay, so also this is the first time I'm teaching a 3-hour lecture for this course. Like, so earlier I have taught this as 2 hour and 1 hour, which was also a bad split. Okay, so let's continue. So far we discussed everything in abstract terms. So let me give you one solid example by using regression, like before we move to the next topic. Okay, so we are going to see a regression example. Okay, now to simulate the expectation with respect to data sets, right? So I'm going to consider 100 different data sets. Okay, each containing n is equal to 25 data points. Okay, so from the sine 2 pi of x curve. So we are going to go back to the same synthetic example, sine 2 pi of x, because in that case we have access to the true function. We can compute e of y given x, right? So in that case, I'm going to consider the same problem, but I'm going to generate 100 different data sets, each having 25 data points. Okay, so let's just say L, which is the total number of data sets, to be 100. Okay, now the model that I'm going to use is going to be a Gaussian basis function regression model. Okay, so we have seen Gaussian basis functions before. So in this case specifically, I'm going to use 24 basis functions. Okay, so 24 Gaussian basis functions as my regression model. Okay, now, so here is what. Oh no, something happened. So well, so here is what the performance would look like. Okay, so now in this case, we are going to use L2 regularization, okay, with least squares. Now, if you think about it, the regularization is going to reduce the variance as much as possible, right? Like, so now when the lambda value is large, it means variance is low, but the bias is very high. Okay, so in the left side, you see for all the 100 data sets, what are the functions that I have learned. Okay, now you take an average of these 100 curves. So what you get is in the right side, and you can see that it is not very close to the green sine function, right? So it's actually very far from the sine function. So even though there was not a lot of variance here, the bias was so high that I get a solution which is not close to the true function. Okay. Now, in the other extreme, where lambda is too small, right? So when lambda is too small, like your variance is going to be high because there is less regularization, and the bias is going to be low. Okay. So in the left side, again, you see a function like 100 output functions, 100 functions, and they are all like curve, like wavy and like wiggly, right? So in the left side, like you see that there is a high variance. Okay, but because this model had less bias, when I average these 100 functions, I'm getting a function which is very close to the true function. Okay. Now, what we are looking for is something in between, right? Like, so we want something which has low bias as well as low variance. Okay, so which would often happen when the lambda value is something in between. Is that clear? So this is another way to look at the hyperparameter lambda. So the lambda is controlling the bias and variance of the model. By tuning this lambda value as a knob, you could reduce bias, increase variance, or increase bias, reduce variance in whatever way you want. Is that clear? Now, as I mentioned before, like this is a that's a synthetic problem where I created this data set, right? Like, so I have access to the true functions, which means I can actually compute the bias and variance empirically, okay? So now the average prediction of all these 100 models, which is h bar of x, is given by 1 over L, summation over L is equal to 1 to L, h L of x, okay? Now this is the average prediction. Okay, so this is an approximation for the average over all possible data sets, but in this case, we only have average over 100 data sets. So then we have the bias term. So bias square is given by 1 over n, summation over n is equal to capital 1 to n, okay? H bar of xn, the average prediction of this model minus the true function, e of y of n given x of n, okay? Now, as I mentioned before, for this particular data set, I can actually compute this because I know the true function, okay? So this gives me the bias. So then we have the variance, right? So the variance is given by summation over n is equal to 1 to capital N, 1 over L, summation over L is equal to 1 to capital L, h L of xn minus h bar. The variance is considering all possible data sets, like how is the performance differing from the data set to the average performance, right? So I can compute all these three quantities empirically, and this is how that is going to look like, okay? Now, if you remember before the break, I showed you a cartoon picture, right? So this real empirical graph looks kind of similar to what we saw. You can see that the variance, okay, so in this case, like the larger the lambda value, more bias, okay? So this is more bias. So you can see that the bias increases and corresponding variance decreases, right? Now, when you combine these two together, bias square plus variance, that is the pink line. You can see this pink line is actually very much correlated to the test error, which is the generalization performance, right? So this numerical example kind of verifies empirically, like whatever abstract things that we discussed is indeed true, okay? Now, I want to conclude with one quick illustration on relationship between many things that we discussed today, okay? So there is true risk, there is empirical risk, okay? And there is also overfitting. Okay, so what is the relationship between all these three, right? So now, let's say this is the complexity of the model. Okay, we know that as the complexity of the model increases, the empirical risk is going to always reduce, because as the model becomes bigger and bigger, more and more complex, you can fit the data set easily, right? So basically your empirical risk will reduce, and at some point it's going to become 0. Okay, so this is my empirical risk. Okay, now my true risk, on the other hand, is not following the same trend. Okay, my true risk will reduce only up to a certain complexity. After that, I will start overfitting. Okay, now this complexity, like whatever you have before this, right? So this is your underfitting region, and this is your overfitting region. Like what you are looking for is something in between, right? Like, so like the situation where you have perfect generalization. Okay, so I think that concludes our discussion on empirical risk minimization. So the goal of the lecture was to tell you, like at a higher level, like what are the different components involved in a machine learning optimization problem, right? Like so there is inherent noise in the system, which we cannot do anything about, and there's bias and variance, like which we can actually play with, right? Like so now this gives us a foundation for studying various algorithms. Okay, so starting from next week. So we are still going to see some fundamentals this week. Okay, is that clear? Okay, so now we are going to jump into the problem of classification. Okay, I think so far we spent a lot of time in regression, like linear regression, nonlinear regression, regression with basis function models, and so on, right? Like, so now probably for the rest of the course, except for 1 or 2 lectures, we are going to focus on classification. Okay, now as usual, like we'll start with some fundamentals, like we'll set the notations on stage, and then like we will get into algorithms. Okay, so now let's consider a K-class classification problem. Okay, so I have C, which could belong to either C1 to Ck. Okay, so normally there are 2 stages in classification. Okay, so first you have inference stage, where you will use the training data to learn a model. Okay, so first you have to learn a model. And the second stage is decision, like where you will learn how to use, well, you will decide how to use this model to make a decision. Okay, so in the inference stage, you will use the data to learn some model which will give you the probability of Ck given X. Okay, so once you have these probabilities, then you're going to use these probabilities to decide the optimal class. Okay, if you go by 0-1 loss function, like as we discussed in statistical decision theory, then the decision stage is simple, right? Like, so what would you do in the decision stage? Anybody? If I have a 0-1 loss, so, and I have the class probabilities P of Ck given X, so how would I decide which class?
To use a boundary decision with 0.5 and compare the results.
Okay. So let's say you have K classes. Okay, so which class would you pick if I give you access to P of Ck given X?
The minimum or the mean of the probability of the class which given.
Wait, is it arg min of the probabilities or arg max of the probabilities? Arg max, right? Like, so you will look for the highest, the most probable class. So that is the decision, right? Like, so now we can actually generalize it. Like, what if I don't have a 0-1 loss function? Like, what if my loss function is a bit more complicated, which has a loss matrix, like the cancer example that we saw, right? Like, so instead of having a loss matrix like this, I could have a loss 0, 0, 1, 1. Instead of this, I could have a loss matrix like this, right? So then I have to calibrate my decision for the risk, right? So the general equation for C of X is given by arg min C belonging to C, summation over K is equal to 1 to capital K, LCK of C, probability of Ck given X is equal to X. Okay, so this is basically the price for classifying an observation belonging to Ck to C. Okay, if the price is high, then you don't want to make mistakes, so you'll be conservative there. Okay, so you will calibrate your decision. So that's why we have a separate decision stage. That's clear? Now, for 0-1 loss function, as we discussed before, it's very simple. C of X is given by arg min over C belonging to C, 1 minus probability of C given X is equal to X, right? Or in other words, this is nothing but arg max C belonging to C, probability of C given X is equal to X. Is that clear? Okay. So now what we have seen so far is, like in any classification problem, there are 2 steps. Like in inference, you compute P of Ck given X. And once you have P of Ck given X, you use the loss matrix and compute the final decision, right? Like, so Now, how do we learn this P of Ck given X? Okay, so well, that is what we are going to see for the next 3-4 weeks. Okay, so we are going to see several algorithms to learn this probability. Okay, so now we can kind of broadly classify all these solutions into 3 major approaches. Okay, so there are 3 approaches to solve classification. And we are going to see examples, several examples for each of these approaches. So the first approach is to learn class conditional densities. Okay, you learn class conditional densities, which is basically P of X given Ck. Okay, what is the probability of seeing this data given this is the class? Okay, and also learn the prior probabilities of the class P of Ck. Okay, once you learn P of X given Ck and P of Ck from the data, then you can use Bayes' theorem. Okay, which will tell you what is P of Ck given X. So P of Ck given X according to Bayes is P of X given Ck, P of Ck divided by P of X. Okay, where P of X, right, I can expand it. So P of Ck divided by summation over K, P of X given Ck, P of Ck. I have just expanded P of X here. Okay, now this is the first approach. You learn P of X given Ck, you learn P of Ck from the data. Then you use the Bayes rule to invert the probabilities. You get P of Ck given X. Okay, now, or you could also directly learn P of X comma Ck, the joint distribution of input and output, and then you can normalize this to obtain P of Ck given X. Okay. Now this idea of first learning the joint distribution or some form of the joint distribution, right? Like, because if you're learning P of X given Ck and P of Ck, in this case, by applying chain rule, like you can construct P of X comma Ck, right? So P of X comma Ck can be written as probability of X given Ck multiplied by P of Ck, right? So both these approaches are in some sense modeling the joint distribution of the data. So, or in other words, instead of trying to model the classification problem, you are really modeling the data. Okay. So once you have a model of the data, the joint distribution, then it is easy for you to ask any question about the data. So you can ask, what is the probability of class being 1, given this is the data point, right? You can ask any queries to this joint distribution, and you're going to get answer, right? So this class of approaches, okay, so is known as generative models. Okay, so we are going to call them as generative models because once you have access to the true model of the distribution, you can generate samples from that. You can easily sample new data points, synthetic data points. Okay, so that is generative models. Now, this whole thing looks very complicated, right? Like, so our goal is not to model the data. Like, sometimes it might be the goal, but often our goal is to just make right prediction, right? Like, I don't care about model of the data, but I just care about making as accurate prediction as possible. Okay, now that is a little bit simplistic than generative models. Okay, so that is the second approach. The second approach is to directly model P of Ck given X. Okay, don't worry about P of X given Ck or P of Ck. You're going to directly model P of Ck given X. Okay, so we are going to call this kind of approaches, the second kind of approaches, as discriminative models. Okay, so they are discriminative because once you have the class conditional probability, so once you have the posterior probabilities of the classes, you can discriminate the data point into one of the classes, right? So they can only discriminate, they cannot generate because you're not modeling the data distribution. I think after 1 hour, it's really difficult. Okay. So that is discriminative model. Okay. Now, one can do even simpler. Why care about probabilities? Like, what if I can construct a model which, given X, just directly tells me what is the class? Okay. So, or in other words, there is no probabilistic interpretation. Like, I have a scoring function which tells, oh, this is the class. If you ask me what is the probability of this class, I don't have an answer. Okay. So that is the third class of models. We are going to call this as discriminant-based models. Okay. So the idea of discriminant-based models is you just have a function f of x, okay, which directly maps x to class label. Okay. We are going to call these functions as discriminant functions. Okay. So now, if I have to summarize, there is a spectrum of classification algorithms. Okay. So in one end, you have generative models. Okay. So generative models are going to model probability of x comma ck, which is kind of an overkill in a lot of applications because we don't care about this. Like, we only care about p of ck given x. Okay. So the next group in the spectrum is modeling p of ck given x. Okay. Now, if you think about it, in the case of generative models, like, you have p of x given ck. From this, you will compute p of ck given x, and from this, you will compute a ck. Right? Now, the discriminative models eliminate a step. They directly model p of ck given x and compute a ck from that. So this is the decision function. This is the decision stage. Right? So this is also the decision stage. Right? Now, in the other end of the spectrum, okay, this is discriminative model. Okay. In the other end of the spectrum, we have discriminant-based models. Okay. Which is basically f of x is equal to ck. Now you can see that this model even skipped the p of ck given x stage. It was directly giving me the class function. Okay. Now, there are advantages and disadvantages for picking one of these. Okay. So probably this is not the time to discuss that. Like, so first we are going to see some example algorithms for each of these. Then you will start appreciating like which model to use when. Okay. But after a few weeks, we are going to come back to this spectrum and talk in detail about like how that like they vary over, like how the advantages and disadvantages differ. Okay, after we have seen some example algorithms. Is that clear? So any questions so far? There is a question. So are the lecture notes for this part out? Okay, well, I'm sorry I forgot to update it in the schedule, but the notes are out even last week itself, like I told in the last lecture. So if you were there in the last lecture, like then you know that the lecture notes were there. So always check the notes folder. The folder has all the notes. Like I think it has even next week's notes. Okay. Okay. So any question so far? Yeah.
I know that you will come back to this, but could you give me an example of this discriminant-based function, this model? I know that, for example, logistic regression is the second one. That one is based rule-based classification, but this one, what? I don't know.
Okay, I know this is jumping too much, but to give you an example, support vector machines are discriminant-based. Okay, so let's continue. So first we are going to talk about. Okay, so I think for today's lecture we will mostly focus on the geometric interpretation of the decision surfaces. Okay, so when I have a classification problem, I have a decision boundary, right? So today we are just going to talk about the decision boundary and what are the characteristics of this decision boundary, and how different classifiers are going to have different decision boundaries. Okay, so as usual, we will start with linear classification and slowly move towards nonlinear methods in the future. Okay, so now to make things even simpler, we are going to consider a two-class problem. Okay, so consider a two-class problem. Okay, let me show you an example. Like for example, let's say a bunch of circles and a bunch of crosses. I want to classify these circles from crosses. Okay, in this case, it looks like a very simple problem, right? Like so, they are far separated. So I can give you a new data point, and you can easily tell whether it is circle or cross, right? So now, when I do a classification, when I learn a classification, the classification model here, it is going to draw a decision boundary, right? Like so, for example, if you are using a linear model, then the linear model will have a line which is separating these two, right? So we are going to call this line as the decision boundary or decision surface. Okay, now this decision boundary separates two regions. Okay, now this region, right? So this is the decision region for class cross. Okay, similarly, this part is the decision region for class circles. Is that clear? Now, when I have a linear model, my decision boundary is going to be always linear. Okay, so when I have a two-dimensional data, my decision boundary is going to be a line. When I have a d-dimensional data, okay, a d-dimensional data, my decision boundary is going to be a d minus one dimensional hyperplane. So in 1D it's a line, in 2D it's a plane, in ND it's a hyperplane. Okay, so I can only fit planes if I have a linear model. So as you can imagine, it's a very it's equivalent to linear regression. Like in linear regression, like just like how with simple W0 plus W1x, you can always only fit lines, right? Like not anything more than lines. In classification with linear models, you can always only fit planes, okay, not more than planes. Is that clear? Now, the problem that we are going to face might be of any nature, right? Like so, for example, like the previous example that I showed you, where like you have a bunch of things which are well separated, right? So we are going to classify problems into two categories, okay? Any problem where I can just use a linear model and get perfect performance. Okay, for example, in this case, I can just draw a line and it gives me 100% accuracy, right? So we're going to call these kind of problems as linearly separable problems. Okay, now these are easy problems to solve because you only need a linear model. Okay, now as you can imagine, most of the real life problems are not going to be in this category. So they're going to be in the second category, which is category of non-linearly separable problems. Okay, so for like one example I can give is, let's say I have something like this. Okay, this is my data. Now, how would I draw a line or a function which separates these two data sets? Like, so one possible thing that you can think of is something like this, right? Now, this is definitely not linear. This is a non-linear curve, right? So now, any problem where you can draw a non-linear curve, like you fit a non-linear curve which is going to divide, which is going to solve the problem, right? Like, so these are non-linear, let's just call it not linearly separable problems, okay? As you can imagine, if you use a linear model in a not linearly separable problem, you're going to have very high error, right? So that is why we are looking for more and more non-linear models. Is that clear? Okay. Now let's talk about the target variable for classification. Okay. Now, in the case of regression, the target variable was simple, right? Like it is just a real number. So t belonging to real value, right? So you had a real number that you want to predict, so you can easily predict it. But in the case of classification, okay, so your target class C belongs to a bunch of discrete categories, right? Like so C1, C2 to CK. For example, it could be dog, cat, birds, and so on. Okay, so now we deal with mathematical models, which means we cannot use these abstract classes, right? Like, so we have to convert them into some form of numbers, right? So if you have a two-class problem, this is a C1 and C2. One easy way to convert this is like saying, okay, t is equal to 1 for class C1 and t is equal to 0 for class C2. Okay, or in other words, t belongs to either 0 or 1. Okay, now this is an interesting way of setting two-class problem because now t can be considered as just the probability of seeing class 1. Okay, so if I take all values from 0 to 1, okay, so then t is basically probability that the class is C1. But in this case, it so happens that we are taking only the extreme values, zeros and ones. We are not taking anything in between. Okay. Now for two-class problem, this is a good idea. Now what about k-class problem? So let's say I'm in a k-class problem. Okay. So how do I set numerical values for t? So the first option is to say t belongs to 1, 2 to k. I have, let's say, 5 classes. Okay. So I have 5 classes. Let's just give some names. So let's say cat, dog, I don't know, lion, zebra, tiger. Okay, so I found 5 words. Okay, these are the 5 things that I care about. Okay, now one possibility to convert this into numbers is just to say, okay, this is 1, 2, 3, 4, 5, and then try to predict these numbers. Okay, now is this a good approach? Is this a good approach? No. Why?
Because the goal is to, separate the closest item together. So these numbers want to present that.
Okay, so these numbers don't represent the goal. Any other answer? Yeah.
Like our ordering.
Sorry, what?
We are ordering the animals.
Okay, so we are giving some ordering which might not be correct, right? So I think there is a similar answer in the chat. It gives a hierarchy in the data. So in some sense, I'm creating an artificial ordering here, right? Like because when this model, numerical model makes a mistake, let's say instead of saying 3, let's say instead of saying 4, okay? So let's say the correct answer is 4. The model is going to make some mistake, which means it could either call 4 as 5 or 3. But it is very rare that it is going to mistake 4 for 1, right? So in some sense, this kind of numbering scheme tells that these two are closer than these two. But in reality, that is not true. In reality, all the 5 classes are equally distant, okay? Now, this is creating artificial distance, which is kind of bad, okay? Yeah, question?
Yeah, I just want to know, is there some situations where this artificial distance would be preferable or
good point.
treating the classes with equal distance?
Okay, so is there some situations where this is not a bad thing, it's actually a good thing? Any, okay, yeah?
For ratings or agreement scores, like very likely, somewhat likely, neutral, and whatnot.
Yeah, so when you have, okay, any target variable which is ordinal, okay, like where there is an ordering in the classes itself, like rating 1 to 5, right? So, or age groups, like you're considering people who are kids, youth, middle-aged, old, right? Like, so now there is an ordering. So anything which has an order, like an ordinal target variable, this is actually a good idea. Okay, so you do have use case for this. But in general, like for most of the problems that we care about, like so there won't be any orderings. Like so, for example, image classification, where you have 100 classes of images, like right. Like, so or what else? Like so, predicting the next word that you're going to type in your iPhone, right? Like so. Now, so these doesn't have a lot of order. Well, of course, there is always structure, right? Like so, for example, like there might be structure in the image classes, like so, like you will not confuse dog with elephant, right? Like so, you will probably confuse dog with I don't know. I don't want to sound stupid, but maybe a fox, like so something which is very close to dog, right? Like so, so there is some structure. But when we are looking for like general purpose algorithms, like so it is very difficult to exploit these structures. So it is better to be as simplistic as possible. So the simplest case here is not to use the structure. Okay. Now, if I don't use the structure, then what would be a better way to represent the classes, right? So what we will commonly use is known as 1 of k coding scheme. Okay, or you might also seen this in many other courses as one-hot encoding. Okay, so what is a one-hot encoding? Like if you have k is equal to 5 classes, let's go to the same previous example like cat, dog, zebra, lion, tiger, right? So instead of calling these as 1, 2, 3, 4, 5, I'm going to give a vector representation for them. Okay, so I'm going to call cat as 1, 0, 0, 0, 0. Okay, I'm going to consider dog to be 0, 1, 0, 0, 0. I'm going to consider zebra to be 0, 0, 1, 0, 0. Lion to be 0, 0, 0, 1, 0. And tiger to be 0, 0, 0. Is that clear? Now, in this case, the advantage is if you compute the distance between all these 5, it is equidistant. Okay. Now, instead of predicting one number, we are predicting 5 different numbers. Okay. Now, there is also probabilistic interpretation for this. Like each column represents the probability of one class. Right. So now, for example, I want to predict one of these 5 numbers, right? So I can predict a number. I can predict a vector which looks like this: 0.2, 0.3, 0.1, 0.2, 0.2. Okay. Now each entry of this vector could be considered as probability of predicting that class. Okay. Now, well, in this case, I have normalized it myself, but we are going to talk about how to do this very soon. But in this case, like I can just say that, okay, the probability of the second class is very high, so I'm going to classify this as a dog. Is that clear? Any questions about the one-hot encoding? Any questions in the chat? No. Okay. Okay. So I think so far I have established all the terminologies that we need. So we talked about 3 approaches for classification. We talked about the decision boundary. We talked about linear model and what can a linear model do. We also talked about linearly separable and not linearly separable problems, and finally how to encode your classes, right? So now let's get into the geometrical intuitions behind decision boundaries. So again, bad timing, so let's see. So to do that, like we're going to study discriminant functions, okay? Now, discriminant functions takes an input vector let's say X, and assigns it to one of K classes, denoted as CK. So this is the third class of classifiers, right? Like, so discriminant-based models. So where you have a discriminant function which takes the input X and assigns it to one of the K classes, denoted as CK. Okay. Now we are going to consider only linear discriminants today, which means the decision surface is going to be hyperplane. Okay. Again, for easy visualization, let's start with two-class problem. Okay. In two-class problem, a very simple discriminant function is basically y of x is equal to w transpose x plus w0. Okay. So we have already seen this before in regression, but here we are seeing it for classification. Okay. Now this w is the weight vector, and w0 is the bias. Right. Now we need a way to tell what class it is, and there is no probability here, right? So this is like non-probabilistic model. So one way to do that is if y of x is greater than or equal to 0, then we are going to say it's class 1, and if y of x is lesser than 0, then we are going to say this is going to be class 2, right? Now, can someone tell me what is the decision boundary for this discriminant model? So my model is y of x is equal to w transpose x plus w0. Now, what would be the equation of the decision boundary?
Y of x is 0.
Y of x is equal to 0, right? So my decision boundary is going to be y of x is equal to 0, right? So in this case, w0 can be considered as a threshold. Okay, so why do I say that? Because if let's say w0 is equal to -7, okay, so then this -7 tells me when the class becomes 1 or 0. Okay, so for example, if w transpose x is greater than -7, then it becomes class 1, right? Similarly, if w transpose x is less than 7, it becomes -7, it becomes class 2, right? So the bias is, so bias had different use in regression case, right? So can someone remind me why did we use bias in regression? In linear regression? So what would happen if you don't use bias in a linear regression?
Error will be high.
Yeah, the error will be high, but why? Yeah? Yes. So if you don't have bias, if you just have wx, right? So in the case of linear regression, all your lines have to go through the origin. So bias was giving you the flexibility, right? So, but in the case of classification, bias has a different use. Like in this case, it acts like a threshold to decide where the classes should lie. Okay, is that clear? Okay, so now I think I have defined what is the discriminant function. I don't want to start with the geometric interpretation because there's only 5 minutes. Okay, so we're going to take a break now and start. Well, let's just take a 15-minute break. So we will start at we will resume at 2:45.